Facebook, and we are recording to the cloud, so it's all yours.
Oh, yeah, I just heard the end of the message. Well, you should all see my screen right now, right? Like
Yep.
seeing a lot of yeses. Okay, great. So yeah, thank you all so much for inviting me or having me here. I'm very excited to talk with you about my favorite topic in astronomy, which is all about gravitational waves. And I'll explain you why, in order to have and observe these gravitational waves, you need those matches made in heaven that we're gonna all talk about. Maybe first some like fun facts about myself. So if you hadn't discovered it from my name, I'm originally from the Netherlands. And for instance, this is actually my favorite cookie, which is a Dutch cookie. It's called a stroopwafel. You can actually buy them here in Massachusetts. So if you haven't ever tried them, I can highly recommend trying one. They're really delicious.
I have a whole box of them.
And usually I would bring them. Like if it's in person, I would definitely bring a bunch of them. I love them. I also love juggling. Usually also when I'm in person, I would definitely demonstrate some stellar things while juggling. I love that. But over Zoom, it doesn't work so well. And the other thing that I love, as I told you, is black holes. And so for me, actually, one of the things that got me into astronomy was really like Stephen Hawking's book, The History of, or like a brief history of time. So I thought that was pretty cool. But we're not going to talk about me today. We're going to talk about exceptional marriages among the stars, which is really the type of research that I do and the stuff that I think is really cool in the universe. But probably when you read this sentence, exceptional marriages among the stars, you might instead think about something like this. So does someone know who these are in this picture?
Johnny Cash and his wife.
Yeah, I hear the right word. So these are, if you haven't recognized it, these are Johnny and June Cash. And do you know something that's special about them?
They can both sing and play guitar.
Very special. Something else regarding relationships and marriage?
They were married forever.
Does someone know how, or want to guess like how long?
Wasn't it 50 plus years, like 53, 54 years?
Close? Anyone's? You can also put it in the chat if you want, but I'll it's a hard hard thing to know. We're not all following the stars, but it's been they've been together for 35 years, at least married, which, you know, among the celebrities in USA and in the world is exceptionally long. Since, as you probably know, although a lot of like celebrities are in couples, most of them don't last for this long, and most of them like break up. And so I hope by the end of today's talk that you'll maybe see or understand why actually in the universe we have the same thing. But in this case, we're not talking about long-lasting marriages or persons, but I'm going to talk about the longest lasting marriages in space, which are actually stars that are in pairs that will eventually, after billions of years, like form pairs of black holes that then can collide and form gravitational waves. So if you'd ask me, I would say these are actually the most exceptional marriages among stars, the stars that lead to a pair of black holes. And here you can like see some artistic image of two black holes that are like staring for me like at the screen. But I'll mention more, like there's a lot of like jargon right now, but I'll mention more what this is all about. But yeah, and why this is so cool is that these black holes that are colliding, if they come from these stars that have been together for billions of years, it means that if we can observe these black holes, that we can actually learn something about the history of our universe and the history of these systems and stars. And so one of the questions why I find this very interesting is that I want to learn about what did our universe look like in the past, and how did these pairs of black holes once upon a time form? And so I'm hoping that by understanding these like long-lasting marriages and these black holes, we can figure that out. And another fun fact that I always am just interested in, like, we can't see these black holes. So how many of these pairs are there in space? And so that's what we will talk about all today. So in the first kind of like half, we'll talk about, what are black holes, what are gravitational waves, how do we observe them? And in the second part, I really want to like go into these long-lasting marriages that are needed to form these pairs of black holes. So we'll start with the first part. And so what are black holes? Maybe that's a good place to start. Well, probably most of you are familiar that like a star like the sun is currently like burning hydrogen, but eventually it will like run out of like its hydrogen fuel. And when it does so, it will kind of die. And what happens for stars like the sun is that they will at some point expand. And so I'm kind of drawing a cartoon here, and here I'm drawing like a little star-shaped star over the sun, but of course the sun doesn't really look like a star-shaped. But in practice, it actually is kind of a sphere that has a core where it's burning hydrogen, or like fusing hydrogen into helium. And then around it, there's kind of an envelope layer where it's just like hydrogen gas that's sitting out there and that's not being burned at this moment. And eventually, when the sun ends its life, what happens is that actually the core kind of contracts a little bit, and the outer layers, as a reaction, kind of like action is reaction, will expand. And the star will actually become this red giant and really swell up and become kind of like 10 or 100 times the size that it originally was. And so this is also what will happen with the sun in like 5 billion years. So we're pretty safe, but eventually it will happen. And then eventually, when it evolves even further, it will kind of like shed away its envelope eventually at the end of its life. And what you're left with is like a tiny compact star, which is the core of the original sun. And you probably also might notice as like a white dwarf, but we're not going to really discuss that. Now, this is a white dwarf, and this is what will happen with the sun. But the sun is not going to make a black hole. So what does make a black hole? Well, it's kind of a similar picture, but in this case, we start with a more massive star. So say something that's kind of like 10 times the mass of the sun or more. In this case, you have a similar structure. So the star has like a little core that is like hot and denser, and then an envelope around it. But now, since the star is hotter and like more massive and hotter, it's also a little bit more blue. So you can also observe this in the night sky. So the bluer stars are often your more massive stars. And in this case, a similar thing happens, but actually the star lives much shorter. So it actually only lives a couple of million years. And then after a million years, it again will expand, often like 1,000 times its current radius. So it will become really, really big. So it's kind of like a super, super red giant. And in this case, there's so much gravity and so much mass involved because it's so massive. Then instead of just like quietly shedding its layers, it eventually like it collapses so much that it like collapses and produces like a supernova. And in that supernova, it like really throws out its layers. And eventually what's left behind is that this core really collapses and forms the black hole. And so if you would ask me, how would you define a black hole, or what is a black hole? I would say a black hole forms when massive stars, so the most massive stars in our universe, die in space. They are extremely compact objects from which no light can escape. I think that's something that probably most of you have heard. And they form in these like energetic explosions that we know as supernova. And just to give you kind of an illustration for like how compact they are, their compactness, or like how small they are, is like the same as if you would have the entire Earth and compress it to the size of a ping pong ball. That's how dense these objects are. And so I think they're pretty cool. Like there's a lot of gravity involved, and I think they're pretty cool objects, like pretty mysterious as well. And they're so mysterious that actually one of the maybe first questions that I would ask is like, how many of these black holes are out there? And so something that you can do is, like it's a pretty bright, clear night tonight. So like later after this talk, I'm going to go outside I'm gonna like look at the night sky, and something that I'll see that, you know, a lot of you hopefully are familiar with is this picture, although maybe not as nice as this picture. And you can see the Milky Way and all these stars, right? And so in our own Milky Way, it's been estimated that we have about 100,000 million stars out there. That's a lot. But now my question to you is, I just told you that you have these massive stars that then die and become black holes. So if you had to estimate how many black holes are there, and you can put your answer in the chat or feel free to like shout it out loud. It's multiple choice, so don't worry. Do you think it's either A, 0, there's no black holes from those massive stars in our own Milky Way? Is it about 10, maybe? Is it perhaps like around 10,000, or do you think it's around like 100 million or so? And I see Tom already put in a guess.
100 million.
I see a lot of these. Does someone want to say something? What I think it's 100 million.
100 million.
And why?
100 million.
Mm-hmm.
Number D.
Yeah, but why do you think so? Why 100 million?
Well, we know there's at least one.
Yeah, so it's probably not A.
Because there's been a lot of supernovas since the galaxy was created.
Hmm.
Well, does every supernova turn into a black hole?
Good question. But I like that thought, right? Like that's actually a good way of kind of trying to estimate it. It's like there's kind of one supernova per 50 years in our Milky Way. So as long as a fraction of them become black holes, you would expect to have like a couple per like maybe one per 100 years or so. Any other thoughts?
Too much helium.
That's an alien. That's our alien answer.
Is it John again? There's someone, I don't know who it is, but there's someone, I can't hear it from the microphone. I'm sorry.
That's Brewster, but I think he's inhaled helium.
Oh, I'm so sorry. But yeah, the answer is correct. It's 100 million, and maybe a fun way to remember it, it's about the same number of kangaroos that are on this Earth. There are about as many kangaroos as black holes in our galaxy, which I think is pretty cute. But yeah, it's about 100 million, and the idea is that basically like 1 out of 1,000 stars or so that is born is massive enough to form a black hole. And these massive stars, they live so short that most of them have already formed a black hole like over the time of our Milky Way. But actually this number is very uncertain. Since we can't observe them, we don't really know how many exactly there are. And there's still a lot of questions to ask, like does every supernova form a black hole? We don't know, and it's one of the big open questions in astronomy today. What you might know is that sometimes we can actually see those black holes. And in most cases, that's because the black hole is surrounded by some gas. So for instance, in this case, it's surrounded by like a disk of material. And in this case, it's like coming, for instance, from another star. And it can eat this material, like some of the material can fall into the black hole. And as this happens, it can produce this light in X-rays. And these are the same X-rays as when you take an X-ray scan. And so what you see is kind of this like eating or this eated material or this disk lighting up in X-rays. And these X-rays we can observe with, for instance, space telescopes here on Earth. And so even though we don't see the black hole directly, we can see that there's a black hole present from this lighting up of the disk. And this is just my little cartoon picture that I drew for you, but there are people that make like professional movies for how this might look like, and that's shown here, and I hope it's going to be visible. So what you see here is this is the companion star. So it's not the black hole or the disk. And this is the star that's kind of feeding the material or like making this ring. And so the video will zoom in and you'll start seeing the disk and kind of the black hole inside that's accreting. Yeah, so this is what lights up. That's the disk. Oh, it's like stalling for me. I don't know. Ah, here you go, sorry. I hope you can see, but it's like this blue disk, and it even produces some jets into space that we're also able to observe. And this is all coming from like the accretion of the material. So that's pretty cool. So, you know, there's a way to observe these cool black holes. And so this was for the first time discovered or observed already back in 1971. And this was the first time they detected these X-rays. And then from those measurements, they could determine that there must be like a black hole that is lighting up this disk, and it's like inside this disk. But you know, 1971, that was kind of when the first X-ray telescopes were alive, and there's now like 50 years that has been passed. And so my next kind of question is, since 1971, astronomers and people have been like looking for those black holes like in our galaxy. And in those like 50 years, so up until 2015, how many of those 100 million stellar mass black holes, so the ones that form from like massive stars, have been observed between 1971 and 2015 using those X-rays? Do you think that's about one? So this first black hole was like is still the only one we've observed. Do you think it's like about a couple of tens, so B? Do you think thousands, or the almost all 100 million that are out there in our galaxy? Feel free to let me know if you have any questions or anything to add, any thoughts. See a couple of thousands. See a couple of B's. Yeah, so with stellar mass black holes, I mean like black holes that form from these stars. So they don't form from like, they're not like the ones that are in the centers of galaxies that are like millions of like solar masses, but the ones that form when a star dies. Any thoughts on why it's I see mostly B or C. Does anyone have a strong feeling about any of those?
They're very hard to detect, and small black holes don't give off many X-rays.
Yeah, that's correct. And so the answer is actually that we have only seen about a couple of tens, which I tried to draw here on this timeline. So we know about like 30 black holes through this method. And the reason is indeed that like they have to be like observable in X-rays, and they can be very faint, but also they need to have this gas around that they need to be eating from in order to light up. And that's actually in most cases, most black holes might not have that companion star or this like accretion or gas around them so that they can light up. And it's just very hard, like it's very hard to still observe this. But that's funny, right? Because we have about 100 millions of black holes, but only a couple of tens of those we have observed. And so if we draw back to this kangaroo analogy, it's kind of as like, I'm like a biologist and I'm studying all these different species of kangaroos, or I'm interested in learning more about kangaroos. But in all those 50 years, I've basically been to one zoo where there's like 30 kangaroos that I've been studying. And so as you can imagine, that's very far from ideal for when you're a scientist, because you want to learn about everything that's out there, and especially like the different things that are out there. So true. But then I have something funny, right? So why did I put 2015 on this timeline? and not just today. Well, in 2015, something special happened that I'm really excited about. Because in 2015, this happened. All of a sudden, we detected all these new pairs of black holes. And actually, by now, we have observed 50 of those. And in this case, it was not through X-rays, because we didn't all of a sudden build a like 100 times better telescope. But instead, what we saw is that in some cases, these black holes can be in pairs. And if they collide, they can produce gravitational waves that we can then observe with this new detector called LIGO that was first built and like observing in 2015. LIGO, yes. But to understand like what really is this different, we kind of first have to go to gravity. So because I was talking about gravitational waves that we can see from these objects. And so if you'd ask me again, I would say that I would define gravity as classically as any object with a mass attracts other objects in space or like here on Earth. And that attracting force is typically what we scientists call gravity. But then you're probably also familiar with this picture, is that Einstein kind of revolutionized our idea or our picture of gravity. And so he came up with this idea that every object, every mass in space, you could kind of see gravity as an object with mass is kind of pulling down on this sheet. And that the gravity that you feel is this kind of natural potential or like hole in the sheet where like a nearby source is attracted to. So for instance, the reason that the moon is orbiting around the Earth is because it's feeling this wiggle in space and this bump in space where it's like attracted to. And so Einstein actually already in 1916, while making up this theory, so 100 years ago, then also theorized that if you have two objects, two masses that are accelerating in space, which means basically like, oh, they're orbiting each other, like they're dancing around each other, that then they would produce actual movement in space. As if you're like dropping a stone in the water, it would like create ripples in space. And this is what he already called gravitational waves. So any masses that accelerate, for instance, by like circling around each other, produce these like waves and ripples in space. And they travel with the speed of light. And this is what we call gravitational waves. And so these were for the first time detected basically 100 years later after Einstein proposed this through the collision of two black holes. And this again is just my little cartoon that I tried to draw. But if you would ask like a more professional artist how this looks like, they draw something like this. So here you see the two black holes, and these green waves are meant to kind of visualize what these gravitational waves might look like. And what you'll see is that they're orbiting each other. So these two black holes are orbiting each other and getting closer and closer. And as they're getting closer, they actually produce like bigger and bigger gravitational waves that are traveling outwards, just like you would have in the water. And now they're colliding. So they collided into one big black holes and releasing kind of the strongest gravitational waves that can now travel through space, just like light, with the speed of light, but it's now space itself that's rippling. And eventually these like ripples can reach the Earth, where it would literally like stretch and squeeze the Earth as it's passing through. Now this is very exaggerated. We wouldn't see or feel it in any of this way, but it does kind of like slightly make the space smaller and bigger. And so people built these detectors called LIGO that in 2015, using lasers and interferometry, for the first time could observe these waves. And these observations look like this. So you're only seeing the end of the merger. So when it's going up, that's when like the black holes collide. So kind of when it's highest here, that's like when the black holes have been collided. And if you translate this to sound, it would kind of sound like whoop. So it kind of like goes up in pitch, because the like black holes get closer and closer and they like accelerate more and more. So you go up, and then eventually when they collide, it's like when it ends. And so people have been calling these like chirps, like the black holes chirp, because it's kind of like sounds or looks like a bird like chirping, like whoop, whoop, which I thought was like pretty funny. And it wasn't only just like cool, but it actually also won them the Nobel Prize for this amazing discovery in 2017 in physics. And those three people, such as Kip Thorne, Barry Barish, and Rainer Weiss, won the Nobel Prize for mostly like building and making LIGO possible to then now, after 50 years of like building this instrument and thinking about this instrument, actually detected these gravitational waves. And I told you they're very tiny. So although any masses in space that accelerates produces gravitational waves. So if I'm like dancing right now, like here in my room, I would produce gravitational waves. However, my waves are extremely small. And to give you an idea of how small these are, for those like most massive and most compact objects, kind of like the strongest gravity objects, still the gravitational waves that pass today, the kind of sensitivity that LIGO has and needs to have in order to measure this is the same like precision that you need to have if you were to measure the height of the biggest lake in the USA, which is like this Lake Superior that I have a photo of. If you would measure the height of that lake and then add 1 liter or like 1 gallon of water, and then measure the difference in height, that adding that like 1 bottle of water, like how much it changed the height, that's the type of precision that you need in order to measure these things, even from those like supermassive like black holes. And so it's extremely small effect of this squeezing and these waves passing by. And that's why you need these like really like tough and difficult instruments in order to like measure this. And I made a funny video where, so today LIGO has observed now 50 pairs of those colliding black holes. So one black hole that collides in a bigger one. And what I'm showing you here is each point is like a pair of those black holes. So here on the like x-axis, I'm showing you the mass of the black hole. So for instance, this one, I can pause it. Oops, sorry. Oh, this is one too far. I'll pause it. I'll pause it. So this is a collision between like a black hole that's 30 times this mass of the sun and one that's kind of like 35. And they collided, so that's why the line is connected. And this is the radius of the black holes. And so actually black holes have a really tight relationship that like their radius scales exactly with the mass. This is called like the Schwarzschild radius. It's not very important. But you can kind of see here that so in this detection, which has this funny name, it was detected in 2015 in September on the 14th. This was like a collision between a 30 and 35 mass black hole that kind of have their radius like of a couple of tens miles. And so if I play the video, you can actually see like all these different collisions and pairs of masses that have been detected. And funny enough, like maybe a fun black hole fun fact is that all those collisions that have been detected have been from black holes that have masses between like a few times the mass of the sun and like 100 times the mass of the sun. And their radii, so their diameter, like the size of those black holes is between the radius of Boston, so a couple tens of miles, and the distance between Boston and New York, which I think is kind of like a cool thing, right? They would fit on the Earth, like they're that small, but that compact. So, next time you take a train from Boston, New York, it's kind of like as if you're traveling through one of those biggest black holes that LIGO detected, which I think is cool. Yeah, and so maybe to just like summarize, I know I used a lot of like, maybe new terms and a lot of like new concepts, but the kind of like only things that, I hope you really take away is the following, namely that black holes form when these massive stars die or end their lives. By these like collapsing in the supernova. And since 2015, scientists can now detect these mergers of black holes through the gravitational waves that they provide once they're colliding. So this is like the formation of a black hole. But since 2015, we can like see those collisions and learn about them and like see how many are out there, for instance, in our own galaxy or like galaxy beyond this. And so that's kind of like the first half of this part where I'll leave you for now with, which is, you know, we now can observe really like more and more of these black holes. And so soon we're really learning now, and we're really starting to see this kind of like population of black holes that are out there, which will hopefully tell us something about how many black holes, for instance, live in space and in our own Milky Way. Thanks to this new probe. And so in the second half, we're now going to discuss how can we use those black holes to like look at the past, but also figure out how they formed. But I kind of want to like midway ask if there's any questions in the meantime.
Excellent. I do have a question. Oh, darn it. Is the mass in a black hole concentrated into a mathematical point or not?
This is a really good question, and actually we don't exactly know, because we don't know what the inside of a black hole looks like, but we think it's, at least as far to our knowledge, like really concentrated in like a small dense point that it really collapses. But we don't know, so there are ideas out there that maybe this collapse stalls at some point, like it's halted by some new quark or like special force that we just are not aware of. And there's people working on it, like for instance, through string theory. But I honestly don't know. Like we think so, but we don't know what really happens inside a black hole. I see William has a question. Can you infer the rotation of black hole from the rotation of its accretion disk? Yeah, so somewhat. So the accretion disk will definitely have rotation, and sometimes it's coupled with like the rotation of the black hole or how fast the black hole is spinning. And so actually the spin of the rotation of the black hole is something that tells us a lot about how it formed. For instance, whether the star that collapsed was also spinning. And so this is really something that a lot of scientists are interested in. And we have measured that for not all black holes. Sometimes it's very difficult to measure this, but we have them for like 10 of those, like 20 or 30 black holes. And with LIGO, you can also find and look at the spin, but of course there's like no gas around there as much.
Hi, Floor. Do black holes die, or do we know if they do, or how that happens if it does?
Great question. So they die in a sense, like I would say this is a little bit dying, that they like collide with another black hole. So like they kind of lose a little bit their identity. There's also some other theories out there that like black holes can vaporize. And it's actually something that Stephen Hawking pondered, is that eventually, but like really in like another many billion years, like we will not live to like see this. They could like so slowly like start losing energy and eventually like kind of evaporate or lose all their energy. But this has not been proven yet, although a lot of people believe that this might happen. And it would not be something that we could really see at the moment, since it would take much longer than we will even be alive. It would be really cool. Yeah, and like most stars spin when they collapse. Also, you kind of have this effect, even if a star spins like a little bit, like most stars spin a little bit. It's really difficult to make a star like not spinning at all. But then when it collapses, you get this like ice skater effect, right? Like if you are rotating and you collapse, you like spin much faster. And so that's why also people think like, oh, so if a star rotates a little bit, like once it collapses to a black hole, it will rotate a lot. But there's actually some questions in like once you make black holes, like whether that rotation really is kind of transformed into the black hole, or whether it kind of can leave the star in other ways. So you can, for instance, imagine like if I am a star and I'm colliding, but I'm producing like a jet, I can like kind of throw out some of that rotation through the jet. And so some people think maybe they lose a lot of their rotation. And maybe black holes spin down. That's another thing that can happen. Yeah, these are great questions. Oh, sorry.
I have a question.
Mm-hmm.
What happens to the energy that's consumed by a black hole?
We think it's like transported into the black hole, so the black hole will like grow a little bit from consuming that energy, if it like really eats it. And otherwise, like if it just like eats it, but it like spits it out, then the energy is like transformed into like a jet or some like X-rays or some luminosity. But yeah, it will be like eaten by the black hole in most cases, and the black hole will grow, and so it will kind of contain more energy than it did before.
Thank you.
I also actually have a question for you to ponder. Because like as I told you, we're going to talk about pairs of black holes and how they collide. And so we're going to talk about how they maybe form from pairs of massive stars, which seems to be like an obvious place to go, because I told you massive stars form black holes when they collide. So maybe you could form a pair of black holes from a pair of massive stars. But then my question is for you. So do you know of any stars that are in pairs or that are at least not single like the sun, either from books, movies, the night sky? Let me know what you think.
Well, most stars, Albireo.
Yeah, I'm not sure I understand the question.
Oh, just like do you know any like names of stars that are not single, or like examples of
Albireo.
Yeah.
Pollux.
Sirius.
I like that one.
Most stars are at least binaries, aren't they?
Good idea. I like that. Oh, I see a lot. Oh, I see Tatooine. I like that one too. Yes, and this is actually an important question for me, right? Like, as I said, like if we want to make those pairs of black holes, one ingredient that I at least would think I need is like pairs of stars in order to form those black holes. So does this happen? Well, you're already going in the right direction. So in order to form these pairs of black holes, we want a pair of stars. And so the kind of like two key questions that I would ask myself is, do we have such pairs of stars? You named a couple of examples, but do we have enough of them to like make this happen frequent enough that we can observe them? And then second of all, actually, once we start with a pair of stars, can they actually stay together forever and form these pairs of black holes? Or do they, in most cases, break up, just like those celebrity pairs? And so you already mentioned a couple of examples, like, do we have some of these pairs of stars? Well, you know, if I have to believe some of the literature that's out there, I know of Tatooine that's been suggested in Star Wars that might be like a pair of stars that if you would live on a planet around it, you would actually see like two sunsets or two sunrises and two stars in the sky. And a system like this actually has been observed recently, and NASA made like a video of it. So this is a video. Here's one star and here's the other star, and this is based on like this is not like the actual observation, but this video is based on a real observation of a pairs of stars that also has a planet around it. So here's the planet, and you'll see like how it's orbiting the two stars. And so if you would live on this planet, you would actually see those like two sunsets and two sunrises, which I think is pretty cool. Yeah, so here we see the orbit.
Wow.
You can see this like a little planet. Like, right. Another example that I love that you mentioned, that I was not surprised, of course, you know all the stars that are out there in the sky, is indeed Sirius, that lives in the constellation Orion. And so this star, even though it looks at the sky, maybe it looks like one light point, if you would like zoom in with a telescope, you could actually see that it's not just one star, but it's actually a pair of stars. And I actually looked through the photos and I saw there's actually that you at least Aaron, who is like part of this club, like made a beautiful picture of also like some of the other cool things you can see in the Orion.
You know Aaron? You know Aaron?
I don't know. I saw this on the webpage. I thought it was
Okay, never mind. Sorry.
I was looking if anyone had like a picture of Sirius itself, but this one was still missing. So you know, should add it to your collection next. I was pretty impressed. But yeah, it's a beautiful constellation. You know, you can observe it most of the time in the night sky, and I think it's pretty cool that just already with the naked eye you can kind of like point to one of those points and be like, hey, that's actually like a double star. But you know, we don't need just one. We would like to have lots of these like pairs of stars. So if I were to ask you, you know, if you would look at the night sky and you see all those like lights, like stars or points of stars in the night sky, how many of those stars that at least to the eye look single are actually not single? Is that about 0 to a quarter of the stars that you can see at the night sky are actually not one star, but if you would zoom in, there would be more? Is it between like a quarter and 50%? Like between half to like 3/4, or is it like almost 100%?
Yeah, see.
$50 to $75.
I see, very convincing. See, I guess I guess you're all like very experienced observers. But it's indeed the right answer. It's always a little bit shocking if you know, people that haven't maybe looked as much at stars, is that it's actually a really, really large amount. And one of the reasons is like in the real universe, if you would just look at a population of stars in the galaxy or at the entire galaxy, you would actually not find this number. You would find a much lower number, maybe around 20 or 30% of the stars are not single. But then actually the most massive stars and the stars that go supernova, they're almost always not single. They're like almost 100% of like the most massive stars are actually in pairs or in like with 3 stars or even more, like 4 stars or so. And since when we look at the night sky, we mostly see the brightest stars, actually most of our night sky stars are not single. And so yeah, in the night sky, if you would look at any like light points, your chances are that you're more likely pointing at one that's not single than a single star, which I think is cool. And in my research, we call these stars, at least the ones that are in pairs, we call them a binary star. And so in my definition, it's like a star system consisting of 2 stars that are orbiting around a common center of mass, or kind of around each other. And they often appear to the naked eye as a single point on the sky. But if you'd actually zoom in with a much better telescope, you would see that it's 2. And as I said, most actually of massive stars are in such a binary system. So that's good news for us, because it means a lot of these massive stars are formed in pairs and form pairs in our universe. And for us, it's only a matter of like keeping them in pairs, and so that they can die as black holes. And you also have like more than binaries, as you know, like you can have 3 or 4 or 5 stars in systems, or even more. And we typically call those like multiples. We have some other fancy names like triples, quadruples, but at some point there's too many names for those things. But they're pretty cool. And so I was actually curious. So, you know, I'm sure you've like all, you know, looked at the night sky and maybe seen some of these like pairs of stars. There's some you can see with already like a small telescope. But I'm curious to see if you actually have a good feeling for what the distance between stars in a binary are versus like stars in just say like, you know, the next star that's like not in the pair, but like just the next star out there. And so I always like to, I prepared a little experiment that you can even do at home especially if you have like little kids. I can highly recommend doing this, and it's so much joy. Like build your own kind of solar system. Because imagine we scale down our universe by an order of 1 to 10 billion. So every like 10 billion miles is now like 1 mile, for instance, or like feet to feet. So you scale down by like a 1 with like 10 zeros. That's a lot. In that case, if you would do so, the size of the sun would become a cabbage. So if you scale down the sun by 10 billion, it becomes the size of a cabbage, and you could like hold it in your hands. And if you would do the same, but with the Earth, it would actually become the size of a grain salt. And the distance between like the Earth and the sun would kind of be like, you know, like 50 feet or so. And it's actually the same size or distance that's between two stars that live in a pair. So if I define like this binary system, I have two stars that are orbiting around each other, and you would scale it down in this like this model of my new universe, you would end up, you know, with two cabbages, and you know, you would have to hold one cabbage at maybe one end of the street and the other cabbage at the other end of the street, and they would like orbit each other, but that's your pair of binary stars. So that's good. And it's the same for like a planet. Like a planet can have maybe the same distance from like the cabbage or like the sun. But of course, there's like different distances, right? Like Jupiter or Earth is like closer or further outer in from the star. But now comes the question for you. So if you were to look at the same scale model, but now instead, you know, we have the sun that's the size of a cabbage. And then it kind of, if the sun was in a pair of stars, the next star would be, you know, a couple feet away. But if I compare this with like the distance to the next star, so the one that's not in a binary, but in this case, for instance, the closest star to our sun is Proxima Centauri. How far do I have to put my cabbage in order to like make my model work? Is that a couple of feet, so I can still do it in my little kitchen or house? Is it B, the length of a soccer field? So I'd have to give the cabbage to someone. They have to like run to the other side of the soccer field, but doable. Is it C, the distance across the USA, which becomes a little bit more problematic, but I can still do it? Or D, the distance from like Boston or so to the moon? Let me know if you have any thoughts or ideas.
Just see again.
I think C.
I've done models that are smaller, and the next star would be in San Francisco. So it has to be the moon.
So the right answer is actually C. It's kind of like the distance between Boston and say California. So like the distance between or like the diameter of the USA, which I think is still pretty cool. But I hope at least like among everything, it kind of gives you this picture of like, oh, you know, for instance, these questions, right? Like if we have these pairs of stars, like how come the sun is not like bumping into like or running into another star that's out there? Well, the answer is that like really the nearest star, like Proxima Centauri, is so far away that it's like so unlikely that they'll ever like meet or like collide or so. But instead, in those like pairs of stars, they can actually be pretty close, right? So it's like maybe a couple 10 of feet. So, you know, you can probably imagine that if you're in a pair of a star and something happens, like one goes supernova, they might like disrupt and like not be in a pair anymore, like break up. And there might also other things that happen. And so C was the right answer. But also a big question is like, yes, maybe we have lots of these pairs of stars. It seems that's the case in our universe. We're very lucky. But the big question instead is, since they're so nearby and so much can happen, like interactions and breakups, how often do they form these pairs of black holes that can collide and produce the gravitational waves? And so the main picture to kind of look at is like have those like two cabbages in mind that are like tens of feet away. But now these like cabbages each are these like massive stars, right? So we start with a pair of massive stars. So each has like a core and an envelope. they live a couple of million years, and then one eventually like goes supernova and becomes this like really red giant, becomes supernova at the end of its life and explodes. But as you can imagine, you know, if you're holding kind of two cabbages 50 feet away, if one of them like makes a big explosion, it's very likely that the other one will not stay with it and like stay in orbit with that star and instead break up. So this one star now goes supernova and becomes a black hole. But actually, in most cases, the stars kind of like break up at that point, and you know, don't stay together, which I would call like a breakup. And so similar to like on Earth, how I would say like, oh, actually most people are in relationships and most celebrities and like star couples are in relationships, but the majority of those break up. And actually in the universe, this happens even more commonly. So although most of these massive stars, they are born in pairs, like 99.99% of them break up during their lifetime, especially during a supernova. However, it's 99.99 and not 100. So in extremely rare cases, they can actually stay forever together and form like continue as a pair with like a black hole and a star and hopefully become this like pair of black holes. And so these everlasting marriages of stars, those are the ones that hopefully can form the pair of black holes. And this again is just a cartoon, but some of the things that can happen, I have like a video that kind of shows it. So this one is made by ASO, and here you see like this pair of massive stars that's like orbiting each other. And what you'll see is because they're so close, besides this like supernova happen, actually other things can happen too. Like some of the material from one star can be eaten by the other star eventually. So in this case, that what you're seeing happening here is that like one star like during its life blows up. So this is your like red giant. And as it blows up, it can actually kind of like throw material onto the other star that can like eat it and like accrete. So it's kind of like a vampire star. It's like sucking some of the material from its companion and like growing and growing. And there's all these kind of like funny things that can happen if you're in a pair of stars that wouldn't happen if you were like alone, like our sun. But eventually the star, like one of the stars will die first and really explode in a supernova, which would look something like this. And you can probably imagine that this would like break up most of the stars.
Can I ask just a one-off question at this point?
Of course.
So a supernova is not necessarily going to destroy the other star completely.
No.
Okay.
No, it in most cases happens because like the supernova is energetic, but it's also like spread out kind of over like a large space still.
Sure.
So it's more that it like breaks up the orbit, but not so much like the star itself, because the star is still kind of like a compact, like you can kind of see this like, oh, like, you know, if you have a cabbage and have another cabbage that like I explode, the cabbage would still survive, but it would maybe kind of like move away or so.
Sure.
Because it's kind of like still compact compared to like the explosion and like what happens at the other cabbage.
Blowing cabbage bits everywhere.
We should do this experiment, you know, if I ever get to the observatory, we should just do this like in real life, like explode some cabbages and see if it like survives or so. Like that would be fun. Not sure if it would be supported, and maybe some police people would like frown upon what's happening, but would be for science, of course. Yeah, no, that would be fun to see if that would still hold the analogy.
Thank you.
Yeah, and so the nice thing is like, so if we go back to this picture, it's yes, we do have such pairs of stars, and we do form these like pairs of black holes, but they only form extremely rarely. So these long-lasting marriages in space that last for these like billions of hours, those are really like the rare exceptions in those like stellar marriages, because the majority of those will still break up. And so the cool thing is that, and the type of research that I do and a lot of people are doing right now, is that we look at those collisions of black holes that we can observe now with LIGO. And by looking at them and like at their properties, we actually try to like understand what maybe the lives were before they became these like pairs of black holes. Because for instance, like the ones that we see tell us a little bit about what the properties of the stars are in order to survive. Because for instance, if we only see the most massive black holes, then can probably assume that like maybe only the most massive stars and pairs of stars can like actually survive and have these long-lasting marriages. So what I'm doing in my real research, like on a daily basis, is kind of like thinking about these questions and like looking at those black holes and those observations and thinking about like, what do we learn about the stars and like the key to these like long-lasting relationships. And so just to kind of like go back and conclude with like, hopefully the couple of few takeaways is that, you know, we now have those gravitational waves through which we can see those colliding pairs of black holes. And this is really an amazing opportunity for us because already now in just a couple of years, it allowed us to see 50 of those black hole merging. Whereas, you know, before it took us 50 years to get kind of to like a sample of 20. And LIGO is only like updating and improving. And so actually we're expecting in the coming like 10 years to really go to like thousands of these detections per year, like really soon. And so this will really like allow astronomers to like look at those black holes, study them and like discover how many there are and like what they're like in our universe. But I hope to also have convinced you that actually by doing that and as a scientist, like looking at like the properties of those black holes, it will eventually tell us something about the lives of these massive stars. And in particularly, what is the key to like a successful marriage in the universe that will provide these like black holes and will make these like massive stars stay together forever. And so if there's anything you maybe want to take away is that black holes form when massive stars die through these like supernovae, where then the core collapses into a black hole. Since 2015, we can now detect those black holes using gravitational waves when these like black holes collide with each other. And although this is very difficult, this is a very exciting field because it's like rapidly growing in the number of detections that will allow us to study these very mysterious sources. In order to like form them, we need those massive stars and we need to put them into pairs of stars so that they can eventually form pairs of black holes. And although pairs of massive stars are very common, it's still extremely rare. And it's really like really difficult as a pair of stars to stay together and form these pairs of black holes. But in rare cases, you have those exceptional marriages and you can make them. And so doing this, we really hope to learn as scientists, like and me personally, I really hope to learn about like all this like mystery in the universe through those cool collisions and those exceptional marriages. And with that, I'll leave you there and just say thank you for being an awesome audience. And let me know if there's any questions or things you want to ask. Thanks.
Well, first, thank you very much. Hooray. That was terrific. Could you convince my friend Fritz, please, that two cabbages separated by 3,000 miles will in fact interact gravitationally?
They do a little bit. Because in the end, gravity still works on like long distances. So for instance, in the Milky Way, all stars in some way like interact with each other, but then there's a lot of like other forces too, right? So they also feel gravity from like the supermassive black hole that's in our center. And there's like rotation in the disk. So they do feel each other in kind of the global sense, but definitely not as strong as say like a pair of stars that like is really orbiting each other, right? So their orbit is really impacted drastically by each other's presence. Like our sun is not orbiting Proxima Centauri.
I have a question. Is there any evidence that any triple black holes have ever orbited each other, like a triple star system like Iota Cassiopeia has ever interacted in that way?
Yeah, that's actually an excellent question. And we think there is some evidence because so some of the black holes that LIGO are detecting are kind of in a forbidden black hole region. So we think that these massive stars, that they never form black holes that are around like 80 times the mass of the sun, but that's like forbidden. They just, if they collapse, they never collapse to that. They just lose more of their mass and they will never collapse to like black holes around 80 solar masses. But LIGO actually detected like 2 events where black holes with such masses were involved. So there was like one black hole of 80 times the mass of the sun and then something else. And so people have theorized that maybe the only way to then form it is indeed by having maybe 2 black holes, like say three black holes in a combination, like in like a closed triple system. 2 of them collide first and form like this like 80 times the mass of the sun black hole, and then colliding with this like smaller black hole. And that's like maybe how you can still form these like forbidden black holes. It's not been proven yet. And whether they form in something that was already a triple as a stars is also not certain, because it might also just be that like if you put a lot of those black holes in a cluster, so you probably have heard of those like star clusters, it might actually be the case that in those clusters you kind of sink the black holes to the center, and there they can kind of like really interact with each other, like with many other black holes, and there form these kind of like triple interactions or so. But yeah, there's a lot of things out there, and it's still a mystery how they form.
Thank you, Vlar. Excellent presentation.
Thanks.
Floor, I just have one quick other one. Neutron stars. We know the evidence for black holes. We've taken pictures of the accretion disk. What's the scientific evidence for neutron stars? That's the first part. And the second part is forming a black hole or a neutron star just a matter of mass, or are there other factors as well?
I love that question, especially since actually neutron stars are like one of my favorite objects, and particularly the collision between a black hole and a neutron star is something that hasn't been observed to date, but I think it's going to be observed like in the coming 5 years, but that's another question. Yeah, so there's some evidence for neutron stars. So first of all, LIGO has seen in the past 5 years 2 cases where 2 neutron stars were colliding and forming like a black hole. And in one case, it was in 2017, there was actually even a pair of neutron stars that collided, and it also produced a lot of light, because if 2 neutron stars collide, it's not like a black hole that sucks up all the light, like some of the material gets kind of like flown away, and this flown away material will like light up, similar to like the X-rays. And so this has been observed, and that's how scientists have really strong evidence that it must have been 2 neutron stars. The other way you can observe these systems is that in some cases, if they're rotating and they kind of just formed, then often you can see them in radio. So these are called like pulsars. And so it's like these neutron stars that are rapidly spinning, and they have like a radio beam. And in some cases we're lucky and this radio beam like passes by Earth like a lighthouse. And in those cases we can pick it up. And we're pretty certain that those are neutron stars as well. And that forms evidence. Now, how you form them is a little bit of mystery. We think the classic idea has always been that you have massive stars, so anything kind of like 10 times more massive than the sun, and at like the lowest range of those massive stars, so everything between 10 and like 20 times the mass of the sun, forms maybe a neutron star, because it's like massive, so it like goes supernova but doesn't fully collapse to a black hole yet. And then if you go more massive, so like above 20 times the mass of the sun, you're really like completely collapse and form a black hole. But this is not, we're not certain about this yet, whether this is really the way it works.
With your permission, I'm going to stop your share so we can see each other, if that's all
No,
right.
of course. I can also stop it.
Yes, all right.
Yes, yes.
Well, my butt's sitting up.
No, that's not.
And yeah, I'll maybe put more happy faces on my black holes.
Except when they're about to collide.
Yeah.
Are you part of the LIGO collaboration, or are you just working like independently but work with them?
Yeah, more the latter. So I'm not part of the LIGO collaboration itself, so I don't know their secrets, but I use their data, and I work like a lot of my colleagues and collaborators are indeed like the LIGO folks. But often when you work in LIGO, you mostly work on like the instrument and doing like running the data, running the observing, like putting the telescope on, making sure everything works, like doing the data analysis. I work more on like the interpretation. So in my daily life, I actually make models of these stars and like how they evolve. So I have like on my computer a model that models the entire Milky Way and like other galaxies, and then like looks at how stars evolve, how many of them form black holes, and kind of answering these questions as like how many black holes are in our Milky Way, how many black holes collide, and how many stay in pairs. But I do more the theory side than the actual observing. So not a LIGO member yet, yeah.
Flora, I have a question. Hopefully my audio is working this time. So what's your opinion on primordial black holes?
Oh, so that's an excellent question. So for people who don't know, primordial black holes are, well, there's lots of different theories, like what exactly they are or how they are created. But kind of the main ideas are that either at the beginning of the universe, you have some type of matter, so maybe dark matter or other types of like big gases that just kind of like spontaneously collapse, just because your universe is so small and there's a lot of like instabilities that like some of these masses, instead of forming stars, what usually happens when like clouds collapse, they instantaneously formed, for instance, black holes. And so I think those ideas are extremely interesting. It's interesting that like the kind of the masses that are needed for that are kind of exactly around the black hole masses that could also explain dark matter. So I think that's kind of like a cool thing that you could kind of explain maybe both with the same theory. But it's still something that we have never observed or don't have direct evidence for. So I think LIGO is going to help, because LIGO might find some evidence that can only be explained with those type of black holes. For instance, if they're like really, really massive, like you can probably only create them in that way. Or if they, if you really see they're really coming from the early universe. But it's hard to like tell now whether that's the answer.
So you're kind of 50-50 on the whole thing, right? You
I think
you wouldn't bet one way or the other?
I think I would bet more on the non-way. So I think I'm like 30-70 in like maybe not primordial, but I think like actually in 10 years or so, like folks are thinking of building the Einstein telescope, and it's gonna be like a LIGO, but like much more sensitive than LIGO, which would actually be able to probe like really far, like detect those black hole mergers like really deep into the universe, like up till like the beginning of the universe. And I think that's really gonna be a test bed for this theory, because if this is happening and if these black holes are there, you would definitely see them as you go like further back in our universe history. I would like bet for 25%. I wouldn't bet like $100, maybe like $10 or so on their existence.
Flora, did you get your sweatshirt okay, and is it the right size?
Yeah, thank you so much. I will actually, I should shoot a photo when I'm wearing it for the
Okay,
fan
good.
club.
Now, this is something that all of you guys probably know, but I have no idea. What is the distribution of black holes across the universe?
Like in their location or in their masses?
Yeah, in their location. Are they equally distributed?
That's a good question. We're not entirely sure. We think they kind of follow where stars are formed. So where you would have a lot of stars, you would have a lot of black holes. So, maybe in our Milky Way, like especially the places where there used to be a lot of star formation. So we're kind of like in the early times of the Milky Way, there's a lot of black hole, like a lot of star formation. You form a lot of massive stars, and then those massive stars form black holes. But some people think, if these always form in these pairs of stars and then one explodes and the binary system disrupts, it might actually be that this like black hole is like kind of flung away, like it's like kind of has some velocity and like is like running away. And so it might actually be that like some of these black holes kind of like escape our galaxy, or at least are wandering around as like single black holes in our galaxy and might be like flying by or so. Like the chance of like actually like interacting or like bumping into them is going to be very low, but it might well be that like all of a sudden we see a black hole like flying in front of some star. People are looking for that, but we don't know. Like this is so hard because they're invisible that it's hard to estimate how often that really happens.
All right, well, we're getting on. Thank you so much again for a wonderful talk. And thank you for the link to the notices of when we're going to get other people passing through Cambridge. That's always good to know. So thanks for coming.
Thank you.
Thanks,
Thank
Floor.
you very much.
Yeah, thanks so much. If you have any questions, feel free to shoot me an email or anything. Very happy to help.
And listen, if anything wonderful happens in your research, please come back.
Absolutely.
Thank you. Mike, got quite a hole above your.
Thanks for a good show, Mike.
Thank you.
All right.
Thanks.
way
Good
to
night,
go.
everybody.
All right, good night, everybody. Thanks again, Floor.
Good
Thank you.
virtual
Good day.
background, Mike.
Thanks, Michael.
Michael,
Thanks, Flora.
Yes.
love that virtual background.
Oh, I got a million of them, Alan.
Literally.
All righty.
All right.
Thanks,
Good
everyone.
night, everybody.
Good night.
Good night.